All right, we're at the second part two of analysis models using Newton's second law. The first video was already 17 minutes, so I wanted to break it into parts so it wasn't one long uh, video. So let's continue. Forces between cars in a train. Train cars are connected by couplers, which are under tension as the locomotive pulls the train. Imagine you're on a train speeding up with a constant acceleration. As you move through the train from the locomotive to the last car, measure the tension in each set of couplers. Does the tension increase, decrease, or stay the same? What do you think? While the train is speeding up, tension decreases from the front of the train to the back. The coupler between the locomotive and the first car must apply enough force to accelerate the rest of the cars. As you move back along the train, each coupler is accelerating less mass behind it. The last coupler has to accelerate only the last cars, and so it is under the least tension. So the answer is the tension decreases. All right, now when the engineer applies the brakes, the couplers are under compression. How does this compression force vary from the locomotive to the last car? Assume only the brakes on the wheels of the engine are applied. So when the brakes are applied, the force again decreases from front to back. The force decreases. The coupler connecting the locomotive to the first car must apply a large force to slow down the rest of the cars, but the final coupler must apply a force large enough to slow down only the last car. All right, let's go to another problem. A car of mass M is on an icy driveway inclined at an angle theta, as in the figure. Part A, find the acceleration of the car assuming the driveway is frictionless. So to conceptualize this, we use the figure to conceptualize the situation. From everyday experience, we know that a car on an icy incline will accelerate down the incline. The same thing happens to a car on a hill with its brakes not set. Now, we categorize the car as a particle under a net force because it accelerates. Furthermore, this example belongs to a very common category of problems in which an object moves under the influence of gravity on an inclined plane. Okay, this is we analyze this. We show the free body diagram for the car. The only forces acting on the car are the normal force N exerted by the inclined plane, which acts perpendicular to the plane, and the gravitational force Fg, which is mg, which acts vertically downward. For problems involving inclined planes, it is convenient to choose the coordinate axis with x along the incline and y perpendicular to it as in the figure. Using similar triangles, we can show that the angle between the gravitational force Fg and the negative y-axis is in it. The negative y-axis in this figure is equal to the angle theta that the incline makes with the horizontal in part A. With these axes, we represent the gravitational force by a component of magnitude mg sine theta along the positive x-axis and one in the magnitude mg cosine theta along the negative y-axis. Our choice of axis results in the car being modeled as a particle under a net force in the x direction and a particle in equilibrium in the y direction. So let's apply these models to the car. Now this means, before we apply the equations, you need to think about this because we automatically think of sine theta as associated with y and cosine theta associated with x. But the way we've oriented our axes, you can see that the part going in the x direction is the side opposite theta. It's the mg sine theta, so it's the opposite. So don't be married to always thinking of sine theta equal to y and cosine theta equal to x. You'll get in trouble. Now let's apply these models to the car. F of x equals mg sine theta equals m a in the x direction, and fy equals the normal minus mg cosine theta equals m acceleration in the y direction. Yeah. Okay, that's not, there shouldn't be any acceleration in the y because it should all be in the x direction. Solve the first equation for A equals g sine theta. So it's a sine theta reduction of gravitational acceleration. And let's see. Okay, we finalize this. And note that the acceleration component AX is independent of the mass of the car. It depends only on the angle of the incline and on G. From equation 2, we conclude that the component of Fg perpendicular to the incline is balanced by the normal force. That is, N equals mg cosine theta. This situation is a case in which the normal force is not equal in magnitude to the weight of the object. It is possible, although inconvenient, to solve the problem with standard horizontal and vertical axes. You may want to try it just for practice. Okay, let's look at part B of this problem. Suppose the car is released from rest at the top of the incline and the distance from the car's front bumper to the bottom of the incline is D. How long does it take the front bumper to reach the bottom of the hill? And what is the car's speed as it arrives? Okay, to conceptualize this, let's imagine the car is sliding down the hill and you use a stopwatch to measure the entire time interval until it reaches the bottom. Now let's categorize this. This part of the problem belongs to kinematics rather than to dynamics, and the acceleration AX is constant. Therefore, you should categorize the car in this part of the problem as a particle under constant acceleration. So again, we have the free body diagram. And to analyze this, we defining the initial position of the front bumper as x initial equals 0, and its final position as x final equals d, and recognizing that vxi, the initial x velocity, is equal to 0, we choose this equation. It should be familiar with it to you. X final equals x initial plus vxi t plus 1/2 at squared. And since we can, xi is the initial position, we can look at it as the origin, it's 0, and vxi, the initial velocity is 0. It reduces to d, the distance x final, is equal to 1/2 axt squared. So we solve for t, and t equals 2d times the acceleration in the x direction, which the square root of it, so it ends up being the square root of 2d times g sine theta. Use the time independent kinematic equation with vxi equals 0 to find the final velocity of the car. Vx final equals 2a xd. This is the equation for vx final squared equals vxi squared plus 2a delta x. In this case, the delta x is d, so it simplifies to v. Since vx initial is 0, it's vx final squared equals 2axd. And so you just take the square root of both sides, and vx final equals to 2ax, the square root of 2axd. Well, ax is g sine theta, and they have its square root of 2. I don't know why they didn't write a 2g sine theta d, but no matter. Maybe it would be confusing in the equation. Okay, we see from the time t at which the car reaches the bottom and its final speed vxf, we see that they're independent of the car's mass as was its acceleration. I'm sorry. Notice that we have combined techniques from chapter 2 with new techniques from this chapter in this example. As we learn more techniques in later chapters, this process of combining analysis models and information from several parts of the book will occur more often. In these cases, we use the analysis model approach to problem solving to help you work your way through new problems. All right, and we're going through 62. What previously solved problem does this situation become if theta equals 90 degrees? Right now, what was 30? Was it 30 degrees and 45, 75, 90 degrees? What do you have? Imagine theta going to 90 degrees in the figure. The inclined plane becomes vertical, and the car is an object in free fall. The question for acceleration becomes ax equals g sine theta equals g sine of 90 degrees equals g. Because sine of 90 is equal to 1. That is indeed the free fall acceleration. We find ax equals g rather than ax equals minus g because we have chosen the positive x-axis to be downward. Notice also that the condition n equals mg cosine theta, mg cosine theta gives us n equals mg cosine 90 degrees, which is equal to 0. The cosine of 90 is equal to 0. That is consistent with the car falling downward next to the vertical plane, in which case there is no contact force between the car and the plane, so there is no normal force. Okay, and now we're gonna look at a different type of problem. Blocks, 2 blocks of masses M1 and M2 with M1 greater than M2 are placed in contact with each other on a frictionless horizontal surface as in the figure. A constant horizontal force F is applied to M1 as shown. Now, let's conceptualize the situation by using the figure and realize that both blocks must experience the same acceleration because they are in contact with each other and remain in contact throughout the motion. Now, we categorize this problem as one involving a particle under a net force because a force is applied to a system of blocks, and we are looking for the acceleration of the system. Okay? Now, let's analyze the first model. The combination of 2 blocks is a single particle under a net force. The sum of the forces in the x direction equals the force times the sum of the masses, m1, m2, times the acceleration in the x direction. Apply Newton's second law to the combination in the x direction to find the acceleration. Acceleration in the x direction is equal to the force divided by the sum of the masses, m1 and m2. Now, the acceleration is the same as that of a single object of mass m1, m2, and subject to the same force. Okay. Determine the magnitude of the contact force between the 2 blocks. Okay, let's conceptualize this. The contact force is internal to the system of 2 blocks. Therefore, we cannot find this force by modeling the whole system as a single particle. The whole system is the 2 blocks. We categorize this as such. Now, consider each of the 2 blocks individually by categorizing each as a particle under a net force. To analyze this, we construct a diagram of forces acting on the object for each block as shown. Okay, we have the 1 block, and got a free body diagram. The contact force is denoted by P. Okay, we construct a diagram of forces acting on the object for each block as shown, where the contact force is denoted by P. From the diagram on the right, we see that the only horizontal force acting on M2 is the contact force P12, the force exerted by M1 on M2, which is directed to the right. We apply Newton's second law to M2. So force in the x is P12 equals M2 acceleration in the x direction. Substitute the values of the acceleration. The force is equal to the sum of the forces. Cat just jumped up on the table. Hopefully she won't come into view, but you never know with these cats. So the acceleration in the x direction is equal to F divided by the sum of the masses. That it is P12, which equals to M2AX, the mass of the second block, times the acceleration in the x direction. That's equal to M2 divided by M1 plus M2 times F. Move your tail. Sorry about that. You got 4 dogs and 3 cats, so it's a zoo over here. Okay, I lost my place. Okay, the results show that the contact force P12 is less than the applied force F. The force required to accelerate block 2 alone must be less than the force required to produce the same acceleration for the 2-block system. Okay. To finalize further, let us check this expression for P12 by considering the force acting on M1 shown in the figure. The horizontal forces acting on M1 are the applied force F to the right and the contact force P21 to the left, the force exerted by M2 on M1. From Newton's third law, P21 is the reaction force to P12, so P21 equals P12. Apply Newton's second law to M1. The force in the x direction for M1 is equal to F minus P21 equals F minus P12 equals M1 times the acceleration in the x direction. Let's solve for P12 and substitute the value of A sub x. P12 equals F minus M1A acceleration in the x direction equals to minus M1 F divided by M1 plus M2, and that equals to M2 M2 divided by M1 plus M2 times F. Okay, I guess that comes from the previous M2, M1, that's M2AX. All right. So our results agree. Let's see if they M2 divided by M1 plus M2 equals times F, and we get the same thing here, M2, M1 plus M2 times F. Okay, now let's imagine that the force F is applied toward the left on the right-hand block of mass M2. Is the magnitude of the force P12 the same as it was when the force was applied toward the right on M1? When the force is applied toward the left on M2, the contact force must accelerate M1. In the original situation, the contact force accelerates M2. Because M1 is greater than M2, more force is required. So the magnitude of P12 is greater than the original situation. It says here, when the force F is applied from the right, we have P12 equals M1 divided by M1 plus M2 times F. This is greater than before because M1 is greater than M2. To see this mathematically, you can modify the equation for the sum of the forces in the x direction to solve for P12. Again, we will take a break from this section and continue next time with more analysis model examples, just so these videos don't get too long.